Okay, let's dive right into this. Welcome to today's explainer, where we are going to take a massive, dense wall of academic text and basically break it down piece by piece. Today we're looking at a brand new mathematical preprint. Now, if you've ever stared at a high-level math paper and just wondered how to even begin decoding the thing, well, you're in the right place. We're going to deconstruct the abstract and the metadata to figure out exactly what the author's achieving here. To ground us before we get too deep, the exact paper we are unpacking today is called Hypergeometric Discriminants by C.A. Joyoung Matsubara Heio. This was published on Archive, which you probably know is the premier open-access repository for math and physics research. And honestly, just by focusing on the structural elements in the abstract of this work, we can uncover a surprisingly clear, compelling narrative of mathematical discovery. And hey, don't let the complex terminology intimidate you, because we've got a very clear roadmap. First, we'll look at the origins of the paper. Then, we'll set the problem by defining the Euler discriminant locus. Next, we'll introduce the hypergeometric system, unpack the logic of proving the singular locus, and finally, look at how the author literally coins a brand new mathematical term.
All right, Section 1, Origins of the Paper and Examining the Metadata.
Now, what's really interesting about this is that before we even read a single sentence, the digital footprint of this paper tells a story. First up, it's supported by the Simons Foundation. That immediately signals this is research backed by a major institution dedicated to pushing the absolute frontiers of basic sciences. Next, look at the scale of this thing, 38 pages. In pure mathematics, a 38-page proof is a seriously heavy piece of architecture. And finally, the timeline. It was submitted in May of 2025, and then a version 2 revision popped up in July 2025, where things like typos were corrected and references were added. You're basically seeing the living, breathing process of peer review and refinement happening in real time.
But perhaps the most telling piece of metadata here is its classification. It's primarily categorized under algebraic geometry, but notice the secondary classification, high-energy physics theory. This is an absolutely crucial clue about why this paper matters. It tells us this isn't just math for math's sake, it's highly cross-disciplinary. The pure geometries being explored here have direct implications for the theoretical frameworks we use to understand fundamental particles and the forces of our universe.
Okay, moving to Section 2, the Euler discriminant locus, where we set the problem.
Every great paper starts by mapping out the current landscape before it completely changes it. The author states that, given a family of varieties, the Euler discriminant locus distinguishes points where the Euler characteristic differs from its generic value. Okay, let's slow down and absorb that. In geometry, a variety is roughly just a set of solutions to a system of polynomial equations. And the Euler characteristic? That's a topological number describing the structure of a space, regardless of how it's bent or stretched. So, the Euler discriminant locus is essentially a map of the exceptions. It's the specific boundary where the standard rules of that shape suddenly break down. The author's planting their flag right there, right in the territory of the exceptions.
Section 3, Introducing the Hypergeometric System. This is the author's primary action.
So the crucial point is, once that landscape is defined, the author brings out their main tool. They tackle that Euler discriminant locus by introducing a new hypergeometric system. But it's not just any system. It's associated with a flat family of very affine, locally complete intersection varieties. I know, right? That is an incredibly dense, awe-inspiring string of terminology. But you really don't need a PhD to grasp the core argument here. The author is essentially saying, to understand those exceptional boundary points, I am building a highly specific, custom-designed mathematical lens, this hypergeometric system, and I'm attaching it to a very well-behaved family of geometric shapes.
That brings us to Section 4, Proving the Singular Locus and Unpacking the Logic.
Let's move to the heavy lifting of those 38 pages and see exactly how this builds step by step. First, as we just saw, they introduce that hypergeometric system. Second, and this is the absolute core of the proof, they prove that the Euler discriminant locus is actually the singular locus of this new system. Basically, they're proving that the boundary of exceptions they wanted to study is the exact same thing as the singularities, the sharp points or infinite peaks, of the new system they just created. And third, they don't stop at just proving they're the same. They establish a concrete formula to actually calculate it, using what are called likelihood equations. They take a totally abstract concept and give it real, calculable substance.
And as part of this massive proof, they established this really beautiful, elegant geometric condition. They proved that this singular locus is purely one codimensional unless it is empty. Now, in extremely simplified terms, one codimensional just means it acts sort of like a wall or a surface within its space. It's not just a scattered, random cloud of points. It has a very specific, structured, wall-like dimension within that larger geometric family. It's a remarkably precise ruling on the nature of these mathematical exceptions.
Which finally brings us to section 5, coining a new term, the true mathematical climax of the paper.
This is it. This is the exact moment in the abstract where all that setup and all those proofs culminate in something entirely new. Right at the end, the author declares, "We coin the term hypergeometric discriminant." That is such a powerful move. By coining a term, the author is telling the community that this specific concept, this unique intersection of Euler characteristics, singular spaces, and new formulas, is significant enough that it deserves its own permanent name in the mathematical lexicon.
And this brilliantly illustrates exactly what they've accomplished. The hypergeometric discriminant is officially defined as the characteristic cycle of that hypergeometric system they introduced. They didn't just point at some mysterious mathematical object in the dark. They named it, they defined its cycle, and they provided the exact formula to solve for it using likelihood equations. They have literally handed theoretical physicists and algebraic geometers a brand new, fully functioning tool.
So, what does this all mean for the bigger picture? Well, we saw at the very beginning that this 38-page paper is explicitly cross-tagged with high-energy physics. By mapping out these complex geometric singularities and giving us the formulas to calculate these new hypergeometric discriminants, the author is actually providing the underlying mathematical architecture that physicists use to describe things like string theory, quantum fields, and the fundamental fabric of reality itself. So the question I want to leave you with today is, how will these newly named, newly calculable hypergeometric formulas reshape our understanding of high-energy physics in the years to come? Thank you so much for joining me on this explainer, and I hope this helped you see the amazing narrative hiding right there inside academic research.